Good evening, everybody. So, this is our last lecture. Amazing. We've gone this whole semester. We've talked a lot about a lot of different statistics, about a lot of different approaches to doing statistics for really a lot of different designs. We've captured, we've talked about what it means to test hypotheses, what it how to evaluate significance, what significance means. We've covered a lot so far this semester, and we're rounding the corner the last into the last leg, which thankfully is a relatively easy leg um, to land on. We're talking about correlations. Now, a lot of people use the word correlation in a lot of different circumstances. In statistics, correlation me- it means one specific thing, but it also means another thing that's more general, which is confusing. Correlation can be both a specific statistic and a design of a study. You'll run a correlational study and you will analyze that study using a correlation. Confusing, quite so. We're focusing on the correlation statistic, which is a product of the correlation design study, but we're not really going to focus too much on that, except for to say that it's not an experiment. The correlation and regression, because we're going to talk correlation, regression, just a little bit of just an introductory flavor of regression, just to kind of like um, capstone on kind of what, just reminding us again what the whole purpose of this thing is, the whole purpose of this course is. Correlation, correlational designs differ from experimental designs in one pretty huge way. And that's the ability to use the dirty C word, cause. You might have heard in your introductory psychology course that correlation does not equal causation. That's a very important phrase to wrap your head around and to really, really think about. It's also really hard to think about because people make decisions that they believe are causal based on correlations all the time. Um, but that yeah, it's just, so I'm digressing into kind of how I would talk about um, correlations in a research methods class, and this is not a research methods class. This is statistics class. The basic point is that the times in which we use correlations differ are different from the times in which we would use, say, t-tests or ANOVAs. Specifically, that we use correlations when we're just trying to look for a relationship among variables. The study that we're doing is trying to establish that there is a mathematical relationship among two variables, or with regression, multiple variables, more than two variables. We'll revisit the flowchart more formally in time, but the flowchart now takes a divergence. And I guess we didn't even talk about the flowchart in two-way. We'll complete all this in due course. Trust me. The major divergence for where correlations and correlational designs live in the flowchart of which statistic to use is that there's no real independent variable or dependent variable. There's two variables, but there's no formal independent variable or dependent variable. And this is kind of where I was starting to go with this idea that there's no causation. In an experiment, we believe that the dependent variable changes as a function of, because of the independent variable. That the dependent variable depends, if you will, on the independent variable. The independent variable is its own thing, and the dependent variable changes as a function of that. This is the effect, this is the cause. The dv is the effect, the iv is the cause. In correlational designs, it's just a relationship. One goes up and the other either goes up or down. And they can go in either direction. And they can it's not necessarily the case that this causes that, but it's just that they're in concert with each other. And so mathematically, the major difference between the statistics you use in experiments, which are t-tests and ANOVAs and correlation, those t-tests and ANOVAs and correlations, is that with t-tests and ANOVAs, the statistics you use for experiments, you need one dependent variable and one dependent variable that is interval ratio and one independent variable that is nominal. For correlations, both variables, I'm not going to call one dependent and the other independent. Both variables, there's two variables, both interval ratio. So the kinds of variables, the kinds of things we're measuring when we run correlations are both measurements that are continuous, both measurements that can take on any number of values. So IQ from 0 to infinity, or functionally from 60 to 145. Number of items you recall on a memory test, what your self-esteem is on a scale from 0 to 1, how much you believe in yourself on a scale from 1 to 10, right? How tall you are, how much do you weigh, how fast did you drive to get to campus, right? You know, about the very first thing that we measured in this class. These are all continuous interval/ratio variables that are fair game for correlation analyses. And we even alluded to correlations when we were first talking about z-scores. So we're going all the way back to z-scores for just a second, just to think. We're not going to be doing too much math here. But remember, when I was teaching you z-scores, and we were believing that knowing a score on one variable helps us to predict what a score is going to be on a second variable. That if I know what you scored on your statistics test, I can calculate a z for your statistics test and then use that z to estimate what the score on a research methods test is going to be. That if I know how much anxiety you have, that's going to tell me what your IQ is. I don't know. The basic point that we practiced a little bit when we were talking about z-scores is that you can use a z-score to take a score on one variable, turn that score into a z-score, turn that z-score into a score on a second variable. That knowing one variable tells us the other variable because they're conceptually related to each other. And so that's kind of the key there, that there's a conceptual relationship between statistics test performance and research methods test performance, that it makes sense that, like, it makes scientific sense. It makes intuitive sense that if you do well in research methods, if you do well in statistics, you're also going to do well in research methods. And that's kind of the underlying idea here. That's the basic framework, the correlation from which correlation grows. That how well you do on one variable can be mathematically reflected in another variable. So in clinical psychology, we typically see that people who have depression and depressive symptoms also tend to have anxiety or symptoms of anxiety. So knowing what knowing what kind of depression symptoms a person has can inform us what people's anxiety symptoms are. And what we did when we went over z-scores was we would take somebody's depression score, turn it into a z, and then plug that z into the mean and population variance for anxiety. But we're going to try something just a little bit new. And this is an exercise, this is something right out of your book. I guess I need to share my screen. So in your book, there's an example in which they have people's depression scores and people's anxiety scores. And what your authors did was they turned the depression raw score into a depression z-score and the anxiety raw score into an anxiety z-score. And take a notice at these z-scores. They're not perfect. They're not exactly the same as they were when we did the z-scores a couple weeks ago. But they're pretty similar. Negative 1.2 and negative 1.67 are both negative. They're both greater than 1. Positive 0.8, positive 5, is kind of close together, still positive. Negative 0.38, negative 0.33, very close together. Same down here. We get a little bit of divergence here. We're 0.75 and negative 0.08. But the point that I'm trying to get you to see is that a lot of these z-scores look pretty similar to these z-scores. The depression z-scores are quite related to the anxiety z-scores. And just grasping that very basic idea is kind of what's at the heart of correlation. That these z-scores are similar to these z-scores, similar-ish, not perfect, not exactly the same thing, because depression and anxiety are different. They have a lot of overlap. They have a lot of things in common. They're not the same thing, or else we wouldn't measure them differently. We wouldn't call depression one thing and anxiety a different thing if the z-scores, if each of these z-scores were exactly the same. So they're close, but they're just a little bit different. There's some overlap conceptually in what depression is and what anxiety is, but they're not perfectly the same. And we can capture mathematically how similar depression and anxiety are by thinking about them in z-scores for just a hot second. specifically if we just do a little bit of math. And so what I'm going to do first is I'm going to talk about what the correlation with the statistic of the correlation is, right? So for every stat that we've learned, I've tried to define what the statistic does. And for correlation, the statistic is R, right? So just kind of similar to ANOVA, it doesn't make a lot of sense that it's a different letter than what you might expect, and I don't have exactly the right story as to why the statistic for correlation is R, but it is. The correlation for statistic is R. And so what the correlation what the R mean what R is, what the test statistic for correlation is it is the average of the product of z-scores of two variables. The average of the product of z-scores of two variables. What does that mean? Average. We've talked. Oh. Average. We've talked a lot this semester about how certain things are averages. Variances are averages. Standard deviations are averages. Anything's an average if you add things together and you divide by the number of things. So already off the bat, that I'm calling a correlation statistic an average, we're on to something. An average of what? An average of a product. Mathematically, a product, multiply two things. Multiply thing number one times thing number two. An average of products. Products of what? Two z-scores. Z-scores of two variables. So if I calculated z-scores for depression, I calculated z-scores for anxiety, I can multiply, I can create products of those z-scores and average them together to get a correlation, statistic. And what that correlation statistic tells me is how similar is depression to anxiety. How much overlap is there between depression and anxiety? How related to depression is anxiety? Correlations tell me how much two variables are related to one another, how similar two variables are to one another, how much knowing something about one variable tells me something about another variable. Let's go back to z-scores for just a hot second and kind of lean into this idea that I'm trying to get you to see. When we first started talking about z-scores, I told you that the whole point of doing a z-score, of calculating a z-score, to be clear, z-scores are for individual people's scores. So your z-score on depression would be where your level of depressive symptoms falls relative to the population mean and population standard deviation. So we can remind ourselves. Z-score equals x minus population mean, which is mu, divided by population standard deviation, which is sigma. I told you and showed you that in order to figure out how rare a score is, how surprising any person's score on some variable is, we need to turn it into a z-score so that we can see how far away from the mean that score is. So we have to do a little bit of math to get a sense of how far any one person's score is from the average. And so now, and so we pulled two principles out of z-scores. The first principle was that we can, yeah, so what we learned was what we figured out in that process was that we can learn a lot of things from z-scores. We can learn whether a person's individual score was above or below the mean simply by whether or not the z-score was positive or negative. If people's z-scores were positive, they were above the mean. If they were negative, they were below the mean, because when you take a big number minus a smaller number, it's positive. A small number minus a bigger number, it's negative. And then we also could understand how far away from the mean was, from the mean the individual score was, based on what the number of, what the actual number, the value of the z-score was. Z-scores closer to 0 are closer to the population mean, and z-scores greater that are bigger are further from the population. This is all review. We've already talked about this. I'm just kind of reviewing to kind of put us in a mindset that's going to be helpful to think about correlations. So a z-score of 0.2 is close to the population mean, but a z-score of 2.2 is far from the population. So why am I bringing this back up again? Because correlations are made up of z-scores. They're the average of two z-scores multiplied by each other. And because of that, we inherit some of the properties of z-scores, specifically that we can, the sign of the correlation coefficient is informative. It tells us something, and the actual value of the correlation coefficient is informative. It tells us something. So just like z-scores, the sign is important, and the actual value of the z-score is important. For correlations, the sign is important, and the actual value is something. Is important. They don't mean exact. You don't interpret the correlation coefficient in exactly the same way. And when I say correlation coefficient, I mean the value of what this mathematical equation gives you. The R value, the statistic you get when you get a correlation, that's called a correlation coefficient. The sign, whether it's positive or negative, and the actual value are both informative in their own way. And so let's kind of tidy up what we started with here. Let's calculate, and I'm not gonna, just like with pretty much everything we've done so far, I'm not gonna ask you to calculate correlations using this formula. I'm just using this formula to help you maybe see what correlations do. So remember, the point of what we're trying to do is to show that a person's score on one variable tells us about their score on another variable, that there's a relationship between depression and anxiety. And we can demonstrate that mathematically. So if we make this smaller, oops. Because you all know how bad I am at doing mental math. I'm gonna pull out my calculator. So what I'm going to do is I'm going to multiply these z-scores together. Negative, well, 1.2 negative times 1.67 negative is 2.004. So write this down. 2.004. And 0.08 times 0.5 is 0.04. 0.38 times 12.54. Now I didn't multiply negative 0.38 times negative 0.33 because a negative times a negative is a positive. So 0.1254. 1.51 times 1.34 is 2.0234. 0.75 times 0.25 is 0.1875, and 0.75 times 0.75 times is a negative 0.08? Yeah. 0.08 negative equals negative 0.06. Now, what I just did was I multiplied all these z-scores times each other. I found the product of each of these z-scores. And now I'm going to find the average of these products by adding all these numbers and dividing by the number of numbers. So 2.004 2.004 plus 0.04 plus 0.1254 plus 2.0234 plus 0.1875 plus 0.06 negative. And we're going to divide by, actually I think we divide by, I have to check the, I think it's n minus 1. Yeah, n minus 1. Okay. Divided by, how many scores do we have? 1, 2, we have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. And we're going to divide, so we're going to divide the sum of all these numbers by 6, by 5, by n minus 1. And we get a correlation of 0.86406. R equals 0.86. So when you average, when you take an average of all the z-scores times of two variables times each other, you get a correlation coefficient. And so what that correlation, this number tells, just like z-scores, tells us two specific things based on, first, the sign, whether the correlation coefficient is positive or negative, and the actual value, how close or far away the correlation is from 0. So first, let's focus on the easier part first, and that is the actual value. Well, I don't think I really hammered home the conceptual thing here. We multiplied a z-score of one variable times another variable. We believed that knowing something about one variable tells us something about another variable. That's why we did this in the first place. That my z-score here and my z-score there have some kind of mathematical relationship to each other. That conceptually, my depression and my anxiety are related to one another. They're similar. There's some overlap in having depression and having anxiety. And the correlation coefficient tells us gives us a mathematical grounding. It expresses mathematically what the overlap between those two variables is, what the similarity between those two variables is. I think that makes a little bit more sense. That knowing that what this correlation coefficient ends up being is informative about how similar two variables are to each other. And they're very, very easy to interpret when you know the rules I'm about to teach you. Because we can immediately get a sense of what the relationship between two variables is, how much overlap there is between depression symptoms and anxiety symptoms once we know how to interpret this number. Now, I'm just going to say something very general before we get into the specifics of what the correlation coefficient does. Just like with t-tests, and just like with ANOVAs, every correlation coefficient has an associated p-value. And also, just like with t-tests and ANOVAs, for correlations, the specific p-value, the p-value depends on the degrees of freedom. We're going to talk about this in the lab. No, sorry, we'll talk about this in a minute. I'm getting ahead of myself. Let's figure out how to interpret this number first. Let's get that out of the way. I'm going to draw a line. And then I'm going to draw another line. I'm going to put 0 in the middle, -1 on this end, and +1 on this end. Why do I do this? Because correlations are bound. They cannot mathematically exceed -1 and +1. So this is a major difference between t-tests and ANOVAs, and even Z's for that instance, where basically they start at a number. So the f values start at 0 and go to positive infinity. T values can go from -infinity to positive infinity. Correlations coefficients, R values, go from -1 to +1. Always. You will never, ever see a correlation coefficient greater than the absolute value of a correlation coefficient will never be greater than 1. All correlations are between -1 and +1. The closer that the absolute value of a correlation coefficient is to 1, so the closer your observed R gets to -1 or +1, the stronger the relationship between two variables. A correlation of exactly one is a perfect relationship. There's a one-to-one relationship that knowing something about one variable tells you everything you need to know about the second variable. Knowing the same with negative one. A correlation of negative one is a perfect correlation. Knowing something about one variable tells you everything you need to know about the second variable. In nature, in practice, these correlations don't exist. There's almost never perfect correlations out there in the world. Most of the time, we're kind of living in this range 0.3, 0.4, 0.5. But when we calculated the correlation between anxiety and depression, found a correlation of 0.86. So it's a strong correlation. So it's high, meaning it's closer to 1. So that means that there's a strong relationship between anxiety and depression. So the closer we get to 1 and the closer we get to negative 1, the stronger the relationship is. So imagine we observed a correlation of right here. Let's just call that, I don't know, 0.41, right? That looks about right by my eyeballing. So 0.86 is a stronger relationship than 0.41. Point 0.64. No, geez. Here, let's do this. Negative 0.64 is a stronger relationship than negative 0.38. Right? So the strength of the relationship increases as the strength of the relationship increases as the value, the absolute value of the correlation coefficient increases. So the closer to negative 1, the stronger the relationship. The closer to 1, the stronger the relationship. Correlations of 0 mean that there is no relationship. That knowing something about depression tells you exactly nothing about the price of eggs in China, right? The old expression, like, what is what does that mean for the price of eggs in China, right? It's the idea that if you know somebody, so if the correlation coefficient we observed between depression and anxiety was 0, that would mean there's no similarity between depression and anxiety. There's no relationship between depression and anxiety. There's no conceptual overlap of any kind. Whereas if we observed a 1 or a negative 1, that means there's perfect overlap, perfect similarity. They're exactly the same thing, but with a different name. right? I mean, think about this as like your family relationships. If if you have a if two people are identical twins, they're going to have a very strong, they're going to have a very high relationship in like genetic makeup. If two people are fraternal twins, they're going to have a still pretty strong relationship in their genetic makeup, but not as high um, as identical twins. If two people are just kind of siblings, they're going to have some overlap in their genetic material, in their genetic makeup, but not as much as fraternal twins, and certainly not as much as identical twins. If two people are cousins, even less so. And then, as you get further away, if you're just looking at like the genetic makeup of people, you really don't have that much of a relationship between, say, your your great 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 grandmother and you. There's not that much genetic overlap. There's there's more genetic overlap than, say, you and some perfect stranger who's not part of your family. That would be, there's no relationship between your genes. Knowing something about your genes does not tell you anything about the other person, right? That's what the so that's how you kind of think about the absolute value of the correlation coefficient. And so that's one half of the puzzle. That's the one thing you learn from the correlation coefficient. The second thing you learn from the correlation coefficient is about the direction of the relationship. Positive correlations mean, positive correlation coefficients indicate that there is a positive direction. There's a positive relationship. Conversely, negative correlation coefficients means that there's a negative direction, a negative relationship. That's not very helpful. What do I mean when I say a positive direction and a negative direction? For positive correlations, as one variable goes up, the other variable goes up. Conversely, if one variable goes down, the other variable goes down. For negative correlations, as one variable goes up, the other variable goes down. Conversely, as one variable goes down, the other variable goes up. This is so crucially important to understand, and it can be pretty bonkers confusing. Positive correlations mean that both variables go in the same direction. Negative correlations mean that the variables go in opposite directions. There's still a relationship. We still know something about the one variable from what we know about the other variable, but what we know is that they go in opposite directions. So let's use some examples. As you drink more, your blood alcohol, the more drinks that you consume, the more your blood alcohol level goes up. As you drink more, your BAC goes up. As you drink more, your ability to drive a car goes down. You become a worse driver. As you become more drunk, you're less able to drive a car. My example of kicking puppies comes back up again. As you get more drunk, you kick more puppies. The less drunk you are, the less puppies you kick. The less drunk you are, the better the better your memory is. The more depressed, so we found a 0.86 for relationship between depression and anxiety. The more depressive symptoms people have, the more anxiety symptoms people have. There's a relationship between self-esteem and self-efficacy. As people with more self-esteem have more self-efficacy. There's a relationship between anxiety and self-esteem. It's a negative relationship. People with more anxiety have less self-esteem. People with lower self-esteem have higher anxiety. People with low depression have low anxiety. Understanding the difference between positive correlations and negative correlations and the directionality of them is crucially important. The strength of the relationship is easy, I think, is easy to grasp. The closer you are to one or negative one, the stronger the relationship. But the whole directionality of the relationship, where as one increases, the other increases, positive correlation. As one decreases, the other decreases, negative relationship. As one increases, the other decreases, negative relationship. As one decreases, the other increases, negative relationship, right? That's crucially important to understand. Crucially important. And we'll probably have to review this a lot. And you're going to have to work a lot to understand this because it's confusing. Go on YouTube. I'll try to find some other links explaining this because it might take a couple times before it really sinks in. But just one more time for posterity's sake. Positive correlations, both variables move in the same direction. I guess we could say, I guess we can change these to be a little bit clearer. I wasn't clear on that. Same, move in same direction versus move in opposite direction. So what I mean move is one variable goes up. How does one variable change as the other variable changes? As one goes up, the other goes up. As one goes down, the other goes down. As one goes up, the other goes down. As one goes down, the other goes up. And this is clearest to see when we look at scatter plots of data. Correlations are typically shown as scatter plots. So on these kinds of graphs, the values increase on the x-axis, starting from the left, and get larger as the values go right. Similarly, on the y-axis, they start low here and get higher as they increase. So a positive correlation would be that both variables move in the same direction. I'm not very good at drawing these little dots, it would seem. Let's erase this big one. So notice something here. There is something going on that, well, so let's first explain what the scatter plot is showing. Scatter plot, each point is a person. This is one person's score. This point is one person's score on the x variable and the corresponding score on the y variable. So their depression is here and their anxiety is here. This person's depression is here, excuse me, and their anxiety is here. So what's happening is that as depression scores get larger, corresponding anxiety scores also get larger. As points get further, as these data points get further, as more distance gets between this vertical line and these data points for the anxiety scores, because really, we can, these are all depression scores. Each dot corresponds to a depression score. As these dots get further and further away, so as these depression scores get further and further away from this vertical line, the y-axis, their anxiety scores also get higher. That right? I'm trying to illustrate this the best I can. That there's that if we were to draw, so what people do is they will draw a line that best describes, that basically cuts through the middle of all these points. If the line goes up like this, if the line increases from the left to the right, that shows a positive relationship. As these values are bigger, these values are bigger. Whoops. Correspondingly, and that's a positive relationship. What I just had there was a positive relationship. As one variable goes up, the other variable goes up. Conversely, now if we have more data points, but they're going in a different direction. As the x variable increases, these y values are smaller. Or to put another way, for these high y values, the ones that are far away from the x-axis, they're very close. They're very low on the x variable. So these people with high anxiety are very low in depression. These people low in anxiety are very high in depression. So the line that best captures these scores would look kind of like that. So as you go from left to right, the line decreases. That's a negative correlation. As one variable gets higher, the other variable gets lower. As one variable increases, the other variable decreases. And so that's the sign. I'm trying to illustrate the sign of the correlation coefficient. But you can also use a scatter plot to illustrate the strength of a relationship. Scatter plots in which kind of look like this. There's no systematic so if I were here, I have this, I have all these data, I have all these data points, but there's no clear direction. As you increase on the x-axis, there's kind of a linear there's the line kind of looks like that, but it's flat. It's the line that best illustrates the way that these points move together is flat. Whereas the last two examples we looked at, there was a very clear and sharp line that went either up or down. So whenever the line that best shows that best shows what these point the best describes how these data points all fit together is a weak correlation, a correlation closer to zero. Whereas this is so much easier to do on an actual whiteboard. If data points look like this, there's a very clear line. There's a very strong line that fits all of these points together, and it is much steeper, right? The last line was flat. This is a flat line. This is a very steep line. If lines are steep, it's a strong correlation. If lines are flat, it's a weak correlation. If lines are steep, it's a correlation for which the value is closer to 1. If lines are flat, it's a value, it's a correlation, the value of the correlation coefficient is closer to 0. If the line increases from right to left, it's a positive correlation. If it decreases from right to left, if If a line increases from left to right, sorry about that, increases from left to right, it is a positive correlation. If it goes down from left to right, it is a negative correlation. Okay. Well, probably, I feel like I'm not at my A game on this. Maybe it's making perfect sense, but I feel like I'm not completely hitting this. So I will put some more resources on Canvas for you to get some more, just get more of a sense understanding what correlation coefficients do. But let's just kind of round this out talking about significance. Because just like with back again, just like with t-tests and ANOVAs, we were comparing means and we were trying to decide whether the difference between the means was significant. That is, that the difference we observed the means was unlikely to be due to chance. We can also judge whether a correlation is significant, whether the relationship between two variables is unlikely to be due to chance. And why am I saying it in that weird backwards way? Unlikely to be due to chance. That's because of p-values. For correlation coefficients, just like with t-tests, just like with ANOVAs, we get an R value, a correlation coefficient, and we get a p-value. The probability that the null is true. Greater correlation coefficients, that is, correlation coefficients that are closer to 1 or negative 1. So, how do we get that? So, just setting this number line back up again. As correlation coefficients get closer to positive 1 and negative 1, p-values get smaller. As R goes up, p-values go down. As the absolute value of R increases, p-values decrease. You might say, you should say, there's a negative relationship between correlation coefficients and p-values. As correlation coefficients get larger, p-values, the probability that the null hypothesis is true, and the null hypothesis for correlations is that there's no relationship between two variables. The alternative hypothesis for correlations is that there is a relationship between two variables. So as you observe, greater R values closer to negative 1 or positive 1, you observe smaller p-values. The probability that the null is true, the probability that there's no relationship between two variables decreases as your correlation coefficient approaches -1 and positive. All right. And I think that is where I'm going to leave it. No, I am going to talk about regression just for 2 minutes, but I'm just going to wrap up because it's kind of a nice capstone for basically the whole course. We just talked about correlation. Correlation compares the relationship between two variables. But regression is more concerned with is a type of correlation that is concerned with all the variance that exists for some concept. What does that mean? Think about something very basic. How do you find what makes a person beautiful? What makes a person attractive to you? There's probably a lot of different features. So there's a lot of components to judging beauty, right? There's a whole it's a big concept. We know we can judge what we can try to figure out what it is that makes a person beautiful. It might by essentially chipping away at this circle of beauty. So what I've done is I've just drawn some overlapping circles on the circle of beauty, right? Not that it might not seem that profound, but what all of these circles are variables that relate to beauty, that explain why people find other people beautiful. It could be that people have pretty faces. It could be that people have nice personalities. It could be that people have nice eyes. It could be that people are funny. So, why am I talking about this? Because let's go back to day one, the very first day we came into this class. We were trying to understand. I started by talking about why we do statistics in the first place. And what I'm trying to illustrate here is that very same concept, but in a new way. There's a lot of variability in beauty, and we can measure beauty by just showing people faces and saying how beautiful is this person, how attractive is this person, and we can understand this feels so disconnected. what what correlation does is it tries to figure out how, if we know how beautiful some person is, what correlation helps us understand is that if people are more beautiful, they're probably more funny. As beauty increases, funniness increases. As beauty increases, the the something about their eyes, the symmetry of their eyes increases, or their eye color or their eye shape, the perfection of their eyes increases. That more the more beautiful people have better personalities. That more beautiful people have more symmetrical faces, right? So there's correlations between this variable and that variable, this variable and that variable, this variable and that variable, this variable and that variable. Regression can calculate all of these correlations at once. I'm not going to ask you to do that. I'm really not going to ask you to think about that in too much more detail. But really, this is kind of the whole capstone of the course. There's all this, there's so many things that make a person beautiful. And we can measure some of those things that make a person beautiful. And we know we've measured something that makes a person beautiful whenever that concept takes a chunk out of, or over, whenever the circle for that variable overlaps with the circle for beauty. Whenever the circle, because there is some overlap between the the color and the shape of people's eyes, and and the concept of beauty, that eyes explains some of the shape and color of somebody's eyes is one of the reasons why a person might find another person beautiful, right? The whole point that I'm trying badly to illustrate here is that this is what statistics does. And we do this all the time. We do this intuitively. And at this point in the semester, we've gotten to the point again where we're doing something intuitive. I'm trying to explain something formally that we do intuitively. We make all these judgments intuitively about how beautiful people are. And I'm using beauty as an example because I've used this previously when trying to explain what regression does. But there's any variable. The whole point of statistics is trying to figure out what variables are important to overlap, what variables are important to take chunks out of another variable, and how much these variables overlap corresponds to the strength of that relationship. It corresponds to how important the eyes are. There's more overlap between face and beauty than eyes and beauty. There's a lot of overlap between personality and beauty. There's a lot of overlap between funniness and beauty, right? And so regression just basically takes a bunch of correlations at one time, all in the hope of trying to capture a lot of variance at one time using a lot of different variables. And I'm going to stop rambling about that now, because I feel like I did a very bad job. Again, it's quite hard to just sit here and to try to talk about these concepts as if I'm talking to you when I'm not talking to you. Because I feel like that I could have gotten to a better place if we would have been in a conversation with this. Anyway, not important. What is important? Correlations. We talked about really what correlations boil down to is understanding what the sign means and what the value of the correlation is. As always, if something, and I'm sure I know this was a confusing lecture. I'm sorry for that. I'll find some additional supporting material to try to help you understand correlations a little bit better. But I kind of glossed over the hypothesis testing aspect of correlations because it you get a correlation coefficient, you get a p-value, and you make the same decisions that we've been making all semester. So what's really different is just interpreting the actual number, because this is the first time where the number, the actual statistical number, is meaningful and useful when it comes to a statistic that we run. So for correlations, really the take home message is understand what the sign means, whether it's positive or negative, and understand what the actual value of the correlation means. And we'll try to review regression in the lab for this when I'm back. I'm not holding you very responsible at all for regression because it was supposed to kind of be a, hey, this is wrapping up kind of everything that we've talked about, and I did a bad job. Sorry about that. So I'm going to stop rambling and say once again, please let me know if you have any questions. Look at some of the other materials I'll make available to you, and we will clear this up when I get back. All right. Have a good night.